You know, we're surrounded by these incredible, invisible forces that build literally everything around us, from the salt on your fries to the rocks deep in the earth. Today, we're going to pull back the curtain on one of the most powerful of these forces, the ionic bond. So think about this for a second. You can grab a paperclip, right? And you can bend it, twist it, make it into whatever shape you want. But have you ever tried to do that to a salt crystal? If you try, it just shatters. Why is that? What's the difference?
Well, the answer is all about the glue holding them together. We have to zoom way, way in, down to the atomic level, to see these powerful, invisible attractions that are responsible for pretty much everything.
So, where does our story begin? It all starts with a simple, universal desire that pretty much governs all of chemistry: this constant quest for stability.
You see, most atoms out there, they're not really happy just hanging out by themselves. They're kind of restless, reactive. They exist in this unstable state, and they're always looking for a way to settle down and find a more stable arrangement.
So what's the goal? What is this perfectly stable state that they're all chasing? Well, for most of them, it's something called the octet rule. It's a really simple but super important idea. Atoms just feel complete when they have 8 electrons in their outermost shell. That's their happy place.
Think of it like a cosmic game of cards where the winning hand is a full set of 8. If an atom has 7, or if it has 1 extra, it's not stable. It's going to do whatever it can, make deals, trade with other atoms to get to that magic number 8. This is the engine that drives all chemical bonding.
Okay, so how do they do it? How do they get that full outer shell? Well, one of the most dramatic ways is through a complete total giveaway of electrons. This is where we see a brand new kind of powerful bond being built. And for this, we're going to use the most famous example there is, one you've definitely got in your kitchen: sodium chloride. Yep, regular old table salt. It is the perfect case study for this whole process. So check this out. It's like these 2 atoms were made for each other. Sodium has this one single electron in its outer shell that it's just dying to get rid of. And chlorine, it has 7. It is so close, it just needs 1 more to be complete. It's a perfect match. So sodium doesn't share, no. It transfers its electron, gives it away completely to chlorine. And when it does that, sodium becomes positively charged, and chlorine becomes negatively charged. And this, right here, this is the whole game. We just created 2 ions with opposite charges. And what do opposites do? They attract. That super strong electrostatic pull between the positive sodium and the negative chlorine, that is the ionic bond. But wait, the story doesn't just end with one happy couple of ions. This powerful attraction has much, much bigger plans. It's an architect. See, that attraction, that pull, it's not just a one-on-one thing. It's a force that radiates out in every single direction, pulling in all the neighbors. So a single positive sodium ion isn't just attracted to one negative chlorine ion. It's pulling on all the negative ions around it. And each of those negative ions is pulling on all the positive ions around them. What you get is this massive, beautiful, perfectly ordered 3D structure of alternating positive and negative ions. And that structure, that's what we call a crystal lattice. This is that invisible architecture we talked about at the beginning. And believe it or not, we can actually measure the strength of this lattice. There's a value for it. It's called lattice enthalpy, and it's basically the amount of energy that gets released when all those ions snap together into place. It's a direct measurement of how ridiculously strong that crystal is.
And for our good friend sodium chloride, that number is a whopping negative 787 kilojoules per mole. That huge negative number tells you an enormous amount of energy was released, which means the bonds holding that crystal together are incredibly strong. It takes a ton of energy to break them apart.
So, okay, we have this microscopic architecture, but what does it all mean in the real world? Well, it turns out this crystal lattice structure is directly responsible for the properties we can actually see and feel.
This table basically explains everything. Remember that huge lattice energy? That's why salt has such a high melting point. You have to pump in a ton of heat to break those bonds. And why is it brittle? Well, imagine that perfect lattice. If you hit it hard enough, you can shift one layer over. All of a sudden, you have positives lined up with positives and negatives with negatives. They instantly repel each other with huge force, and the whole thing shatters. And finally, electricity? It only conducts when it's melted or dissolved, because only then are the ions free to move around and carry a charge. When they're locked in that solid lattice, they can't go anywhere.
Now, to really appreciate what makes an ionic bond so unique, it really helps to compare it to its chemical counterpart, the covalent bond.
Let's go back to that paper clip from the beginning. The atoms in that metal, or in something like water, they're held together differently. Instead of one atom stealing an electron from another, they decide to share them.
All right, let's put them head to head. The biggest difference, the number one takeaway, is transferring versus sharing. Ionic bonds are usually between a metal that wants to give up an electron and a nonmetal that wants to take one. Covalent bonds, that's usually two nonmetals who both want electrons, so they have to compromise and share. This leads to those big crystal lattices for ionic compounds, but individual little molecules for covalent ones. And it's why ionic compounds almost always have way higher melting points.
Ultimately, what decides whether atoms transfer or share comes down to a property called electronegativity. It's basically a measure of how strongly an atom pulls on electrons. Think of it like a game of tug-of-war. If one atom is way stronger, a huge difference in electronegativity, it just yanks the electron clean away. That's an ionic bond. But if the two atoms are pretty evenly matched, neither can win, so they're forced to share, and that's a covalent bond.
And that leads us to a really fascinating final thought. Because in the real world, no bond is 100% one or the other. It's more of a spectrum. So the real question is, where exactly on that spectrum does a polite sharing agreement turn into an outright electron theft? It's a blurry line, and it's one that keeps chemists busy exploring the very nature of matter. Thanks for diving in with me on this one.